Hey everyone, and welcome back. In this lecture, I'm going to show you how to uncompress a file that comes in tar.gz format. For Mac and Linux users, Linux especially, this is very simple because this is a very common format. For Windows, it might seem a little strange because it's not typically a format that you see in Windows, but nonetheless, it's still very easy to follow this simple recipe I'm going to show you. Firstly, let's talk about what this type of file is. It looks a little strange because there are two extensions, .tar and .gz. You can think of them as steps. So originally I had this raw file, and then I added the .tar and then I added the .gz. So to uncompress this file, we have to do the reverse and in the opposite order. Now you might wonder, well, what are these two steps? Firstly, the gz stands for gzip, which is the compression algorithm that's used. The tar means that it's possible to join separate files and folders together into the same file, hence the term tar, as in physical tar, which is a sticky substance. Okay, so if we download a tar.gz file, how do we get back to the original contents? I'm going to cover the Mac and Linux use case first, since that's the simplest. So all you need to do is go into the command line, cd into the folder where the file is, and type in tar -xvzf and then the file name. So even though there are two steps, the tar program is going to take care of both steps for you. If you want to know what these arguments mean, you can type in man tar into the command line and read the documentation. So Windows is where students often have problems. The most common scenario is that students only do one of the steps, which is the unzipping, but they don't do the untarring. So one solution is, if you have Cygwin installed, you can just use the same command as on Linux, since Cygwin was designed to give you all the common Linux commands on your Windows machine. Another solution is to use the program 7-zip, which can come in handy for several other file formats as well. You can download it from 7zip.org. Once you've installed it, you'll be able to right-click on the file and select Extract. There are several options for extract, like Extract Files or Extract Here. You can choose the one you want. But notice how the output of this file still ends in .tar. That means you need to do the second step, which is to untar the tarred file. So to do that, you have to right-click on the tar file and again select Extract. Once you've done these two steps, you should have the original files back. So just to reiterate, there are two steps, and for both steps, you just right-click on the file and go to the 7-zip menu and select Extract. Hey everyone, and welcome back to this class. This lecture is about how to write code independently when you're doing machine learning. You always hear me say that the first thing you should try to do when you learn an algorithm is to go and write it up in code by yourself before looking at someone else's code. For some students who are new to machine learning, it's not quite clear how to do that. So this lecture is going to explain the thought process you should go through in hopes that it encourages more people to try to code by themselves. I like to encapsulate this in the phrase, when it's time to code, you must code. So remember this whenever you see some code that demonstrates the concepts we learned in this course. Even if you don't fully understand what's going on, coding and copying examples from others helps you build muscle memory. Sometimes people act like they are going to learn tennis by reading a book about tennis. This is of course obviously not possible. You need to learn some things about tennis which are pure fact and reside in your brain as conscious facts. But then you have to go out and practice those concepts on the tennis court. Once you've exhausted and mastered everything you know so far, then you can learn new techniques. So you have this continuous cycle of learning new techniques and then practicing them. Why is this? Because learning the technique as pure fact doesn't mean you truly understand it. Practicing the technique helps you think about the technique from a different perspective. Practicing again and again leads to new understanding, to learning in the subconscious, which is muscle memory. You must go through this cycle. But some students naively think they are going to read an entire book about tennis and then be a tennis master the first time they try playing. This is very common, especially when all you really need to do is sit there and watch a video and no one can force you to type. A lot of people don't even think to try. So just remember this whenever you see code. When it's time to code, you must code. First, we are going to talk a little bit about why you want to code by yourself. A lot of the time, what an algorithm does or how it works isn't quite clear the first time you learn about it. Every individual will have their own unique background, so they might be familiar with the patterns and know exactly what to do, while some individuals might have questions that no one else has. Sometimes you gloss over details because you assume you know what's going on, when really there are important things you're not considering. So this is how trying to code by yourself can help you. Coding by yourself forces you to think about each and every detail. It forces you to think line by line. You have to be familiar with the data types and the shapes of all your variables, and they all have to fit together properly, kind of like Lego blocks. As an example, you know that in order to do element-wise matrix addition, both matrices have to have the exact same shape. So if you find that they are not the same shape, then one of your previous assumptions was incorrect. So you should go back and correct it. Lego blocks have to follow a specific set of rules in order to fit together properly. If you make incorrect assumptions about how Lego blocks fit together and you try to join them, it's not going to work. Without trying to build things by yourself, you will never discover these details. Let's now talk about how to code by yourself. Consider the supervised machine learning scenario. We know that we're going to have some inputs and some targets, and we want to try to make predictions from the inputs that are very close to the targets. We typically call the inputs X and the targets Y. Sometimes we call the targets T, but for the purpose of this lecture, we'll call the targets Y. Now this next point is a key point. It doesn't actually matter what X is and what Y is. It doesn't matter if you're looking at an e-commerce data set and the columns of X might be time on site, time of day, how many pages the user looked at, and so on. You could just as well be looking at a data set of X-ray images where each column is the pixel intensity of an image. This is the key point. We say all data is the same. When we do linear regression, we don't have different kinds of linear regression for e-commerce and X-ray images. Linear regression is the same algorithm no matter what your data set is. So we say all data is the same. Theoretically, I could give you a data set of X's and Y's and you could train a classification algorithm on it without me even telling you what the X's and Y's mean. You should get very comfortable with this idea. Sometimes people say, well, this isn't practical because I want to do concrete examples. But that's because they're not thinking intelligently. In fact, this is the most practical thing we can do because it means everything we learn, we can apply it to any data set that exists. It means that I can train a model on an e-commerce data set, but I can also train a model on an online advertising data set without learning anything new at all. It's truly the greatest form of lazy programming. Learn something once and apply it to every industry. One great consequence of all data is the same is that there is an unlimited amount of practice opportunity for you. You can download data sets from Kaggle, from Google, from Wikipedia, from Amazon, or from anywhere else and try the algorithms you learned. What this means is, let's say you have a data set you care about more than something we do in class. See, in class we have to use data sets that everybody can understand. For example, text and images. Everybody should know what text and images are. Text and images are just fundamental data types on the web. You probably don't even think about the fact that text and images are data because it's so trivial. In any case, we work with text and images a lot because everybody understands them. But let's say you're a biologist and you know about DNA. You find DNA and genomics really interesting. So you want to use the algorithms we learn on that. Well, that's great and you should totally do it. Remember, all data is the same. So all you need to do is convert your data into the appropriate X's and Y's, to plug into our machine learning algorithms. The downside is we most likely won't talk about DNA in class unless it's a very simple example, because most computer scientists are not biologists too. So they don't know what DNA is. They don't understand the specifics. So an example wouldn't make much sense to them. This is opposed to text and images, which makes sense to everybody. Same goes with any other specialized field like finance, computer networking, cosmology, and so on. So now we can start off from the right place to talk about supervised learning. We have our X's and we have our Y's. What do we do with them? In supervised learning, we know that there are two main things we want to do. We want to do training and we want to do prediction. In scikit-learn, all the models have the same API. It doesn't matter if you're doing logistic regression or decision trees or random forest. All supervised models in scikit-learn have the same two functions, fit and predict. Fitting a model is just a synonym for training a model. If you don't believe me, you can go look at the scikit documentation yourself. When you're learning about supervised machine learning, what you're really learning is what goes inside these two functions. What are the parameters and how are those parameters learned? That's really what all supervised machine learning is, filling in these two functions. Taking this perspective is going to give your code structure, and it's going to make things much easier to visualize in your head. Let's now do a simple example to solidify this idea. In this example, I'm going to give you an algorithm and you will implement it in code. There are two key points I want to make before I give you the algorithm. First, I'm not going to give you much intuition about how it works. Second, I'm not going to derive the theory behind why it works. The reason I want to mention these two key points is that you should realize you don't need these two pieces of information in order to translate pseudocode into code. A lot of time, these three concepts, intuition, theory, and implementation, work to reinforce each other. The reason I'm focusing on implementation right now is because it's the one people most often miss or think they don't need at all, when really it's an extremely important part of the learning process. Okay, so the pseudocode is as follows. In my predict function, as you already know, I'm going to take in some input data x. My predictions will be y hat equals x times w. You might already recognize this as linear regression. However, forget what you know about linear regression and pretend that this is just some formula I gave you. What I can tell you is that we are creating some kind of regression model. It should be clear from this equation that the parameters of the model are contained in this vector of weights w. I would probably also tell you that w is a vector that's the same size as the number of feature vectors in X. Of course, this must be true in order for the matrix multiply to be valid. This acts as kind of a sanity check so you can make sure everything is making sense. In my fit function, I want to perform this loop some number of times. Since we know from the previous slide that the parameters of the model are contained in w, then it should be clear that inside the fit function, what we want to do is update w. Not surprisingly, that's what's happening here, another good sanity check. Now, because you're already familiar with linear regression, you probably already recognize this as gradient descent. Again, I want you to pretend that you don't know that. But what do you know? You know that iterative algorithms are common in machine learning, and that gradient descent is among the most common. You could probably infer that this is some form of gradient descent, but you don't need to know what it is in order to write it in code. What else do we know? You know what a for loop is, and you know how to write one in Python. You know that X is an n by d matrix containing the input data, and that y is an n-size vector containing the targets. You know that y hat is an n-size vector containing the predictions. You know that w is a d-size vector containing the model parameters. And you know how to add, subtract, and multiply these objects. So we can write this algorithm without even knowing how it works. Of course, a lot about how it works can just be inferred from this formula. Here is what you don't know. You don't know t, the number of times the loop is supposed to run. You don't know eta, the learning rate. This is completely fine. You can't let this lack of knowledge stop you in your tracks. The truth of the matter is, there are going to be situations where you're not told the exact numbers to plug in. In many cases, the answer is going to be, it depends on the problem. The important thing is, you have to get used to the idea of trial and error, and you have to make educated guesses based on what you already know. So what can you do? Well, you know that the learning rate is supposed to be a small number. How small? It depends on the problem. Typically, it's a number less than 1, like 0.1. If that doesn't work, you might try lowering it. Typically, we lower it by factors of 10. So for example, the next learning rate we would try is 10 to the minus 2, 10 to the minus 3, and so on. Typically, in machine learning, whether you're looking at a supervised or unsupervised algorithm, there is an associated cost or objective function that you're trying to minimize. Let's suppose I tell you it's squared error, which is typically what we would use for regression. Well, now you have a way to choose the number of iterations of the loop and the learning rate. How do we do this? So inside your fit function, you would plot the cost as a function of iteration. I always recommend doing this, no matter what algorithm you're looking at. In general, you always want the cost to converge. The pattern you typically see is that there is a steep drop at the beginning, and it slowly flattens out as the number of iterations increases. To choose the number of iterations, you want to stop when the curve is sufficiently flat. You might recognize this as a diminishing return scenario. The returns diminish because at the beginning, we reduce the cost by a lot in just a few iterations. At the end, we can do a lot of iterations, but we reduce the cost by almost nothing. An alternative is, you could use a separate validation set and stop when the validation cost increases, but that is not the focus of this lecture. Unlike the training cost, the validation cost is not guaranteed to decrease at every round, because that is not what we are minimizing with respect to. You can also use this same plot to help improve your learning rate. If the cost explodes or becomes not a number, your learning rate is probably too high. If your cost converges too slowly, you can try increasing your learning rate. So what does your final code look like? Well, we know we want to create a class with at least the predict and fit functions. You don't have to use a class, but I find that it encapsulates the code nicely and provides useful structure. Notice that once you have the algorithm in math, there isn't much work to convert it into NumPy code. You know how to do matrix multiplication, you know how to add, you know how to subtract. These are basic arithmetic operations that I'm sure you know already. If you don't know how to do these in NumPy, then I have a completely free NumPy course on the NumPy stack that you can take. Here is the second part of the code where we actually create an instance of the class and then use it. I've also included the squared error cost function just for completion's sake. What's cool about this template is that it doesn't really change from one algorithm to the next. The structure is basically always going to be this way, at least for supervised learning and unsupervised learning. So as we discussed before, it doesn't matter what algorithm you're implementing, whether it be linear regression, logistic regression, a neural network, and so on. They always have the predict function and the fit function. And learning what goes inside these functions is equivalent to learning the algorithm. So in fact, one way to begin coding is to start with just this boilerplate code and then fill in the blanks. This is what is known in software engineering as test-driven development, or TDD. In test-driven development, we start by writing tests, because number one, your code should always have tests, and number two, writing the test first forces you to think about how you expect your API to work, and it allows you to make sensible design decisions without being distracted by implementation details. So you see how this applies to every machine learning algorithm, not just linear regression. In a lot of my older coding videos, I unfortunately decided to just write the code straight through. This helps some people, but is not ideal for others. In addition, the coding videos will appear without warning. Generally, the lectures appear in the same pattern. First we do theory, and then we do the corresponding code. It pretty much always works this way. So after the theory lecture, you can be pretty sure we are going to implement that theory in code soon, unless it's so simple that it can be an exercise. Now, to avoid treating everyone like they're in kindergarten, I don't have videos telling you that it's time to code. You're all proactive and independent adults, so when you learn some theory, you already know that it's time to try to put that into code by yourself. Sometimes you might get stuck and have no idea what to write in code or what the data set is. In that case, it's fine to watch the next coding lecture, but don't watch it all the way through. Watch just enough so that you know what the general idea is and what we're trying to accomplish, and then try to finish the rest yourself. Now let's say you've watched just enough so that you know what we're trying to do. You know the theory, but you still can't complete the code. At this point, you may want to revisit the lecture theory to make sure you really understood each part. Failing that, you may want to try and get clarification on the discussion board. Failing that, you may want to look at external resources as well. Sometimes you might be missing some important computer science background that I've assumed everyone already knows. That's perfectly fine because everyone has a different background. It's highly encouraged to do your own research, and this is also perfectly normal. It's not a bad thing, it's a good thing. Ask any university student if this is what they do, and they'll tell you that they do it all the time. This builds a level of mental toughness and initiative taking that's important if you want to learn this stuff. There's a lot to learn, and I myself am still learning new things every day. So let's say you've rewatched the theory lecture, you've looked at some external resources on the theory, and you still don't understand how you would put it into code. Well, at this point, there are some great exercises you can do. Watch the coding lecture or look at the full code on GitHub. Go through it and make sure you understand each line. The next step is, without looking at the code again, try to implement it yourself. This by itself is a great learning tool. Many of the algorithms I've learned, I didn't understand them the first time. I learned them by looking at someone else's implementation and dissecting it. I looked at each part and I asked myself, which parts did I get right and which parts did I get wrong? This helps you understand the mistakes you were making previously. The cool thing about implementation is it works backwards too. We go from theory to code, but thinking in the reverse direction, the code actually helps us understand the theory better also. I always say that if you can't implement the code, then you don't understand the theory. So if you can learn the theory 50% of the way, try to implement the code, look at an existing implementation, and then finally get it working, then you can be guaranteed that you now know more than just 50% of the theory. The act of coding helped you understand more of the theory than if you had just learned the theory by itself. So implementation helps you understand the theory, but it also helps you understand the intuition as well. Intuition is a tricky thing. In fact, I would go so far as to say it's a trap. In many or maybe even most cases, intuition is built on experience. That means deriving the theory from first principles, or in other words, deriving the theory from facts you already know to be true, and from implementation. Students often want to hear intuition from people with lots of experience, but the problem is that this intuition is built on hindsight. Intuition is often both the first thing and the last thing you want to focus on. You want to have a little bit of intuition at the beginning, so you have some general idea of what you want to accomplish. Then after you learn the theory and implementation, you can reflect on the details and summarize them at a high level. This is real intuition built on hindsight and experience. The big mistake beginners make is that they read some intuition written by someone else who actually has experience when they themselves do not. From an outsider's perspective, it's hard to tell the difference. Why is that? Well, if the beginner can regurgitate the same high-level ideas as the expert, then it would sound like they are also an expert when in fact they are not. There are unfortunately too many courses out there that do this. They want you to feel good that you learned something, and they want to avoid you having to do anything too difficult. And because you can repeat the same high-level intuitions, it actually sounds like you're an expert. So this is why I call it a trap. Knowing intuition not only makes you feel like you know something, it also makes you really confident about this fact. And then because your ego wants to maintain this confidence, you'll start making crazy statements like the theory and implementation are not important because you already understand the intuition. But as you know, this is completely backwards. Let's summarize this lecture, since that was a lot of information to take in. Remember, this lecture is all about how and why you should code by yourself. First, we talked about why. This is because it ensures you are thinking about the details and filling in the blanks using your own pattern recognition skills. It ensures you don't just assume you know what's going on, but that you actually know what's going on. There's a big difference, especially if you're the type of person that likes to assume you know everything. Next, we talked about how. We talked about how all data is the same, and it doesn't really matter what domain or industry your data is from, the same algorithms all apply. Next, we looked at the interfaces to the algorithms, which are also conveniently all the same. So we have a kind of mix and match type of scenario, where we can input any kind of data into any kind of model. For example, you can use linear regression with financial data, or you can use a neural network on ecological data. All data is the same, and all models have the same interface. Next, we talked about a strategy for how to actually apply this. You've probably already seen that we always alternate between theory and code. First, we discuss the theory, and then we implement that in code. Sometimes you might have to go back and revisit the theory, or sometimes you might have to look things up on the internet. That's perfectly normal. This is pretty much the day in the life of a university student. We're trying to build the same level of mental toughness and initiative taking in this course. So the strategy is, stop after you learn the theory and try to code yourself. Sometimes you need a little more detail, so you might want to watch a little bit of the coding lectures to see what's going on, and then try to implement the rest yourself. If you can't get it by yourself, then maybe try watching the whole thing, or looking at the expected result, and then trying to implement it from memory. This by itself is a great learning tool because it allows you to ask yourself, what did I get right and what did I get wrong, so you can understand the mistakes you were making. Finally, it's important to understand the difference between intuition, theory, and implementation, and how they reinforce each other. It's important to not fall into the trap of only understanding intuition, written by someone else, and then assuming that this equates to actually understanding everything. In many cases, it's not about waiting for someone to tell you some nice phrases that trick you into thinking you understand the intuition, but rather you should seek intuition by working through the theory and the implementation. And lastly, don't forget, when it's time to code, you must code. In this lecture, I'm going to talk about Jupyter Notebook. Occasionally, I get this strange question from students asking why I don't do things in Jupyter Notebook. Let me explain why I think this is strange. Firstly, it's my position that it's completely unnecessary and actually doesn't change anything to use Jupyter Notebook or not. Let me repeat that. Using Jupyter Notebook is exactly the same as not using Jupyter Notebook. There's no difference other than the fact that it looks different. In other words, the screen is a different color. Obviously, such a difference is trivial. In this lecture, I'm going to demonstrate how that's the case. One major reason I dislike Jupyter Notebook is because it causes too many students to be unaware of how Python really works. If you're only comfortable inside Notebook, and when you see Python code in a text file or anywhere else, and you get scared or intimidated, that's not good. That Python code that's in the text file is exactly the same as what would be in the notebook. There's really nothing scary about it. Programmers working at real jobs eventually need to write code that's going to be deployed and run automatically. In other words, your final code is going to sit in a Python file that runs by itself without Jupyter Notebook. So if you're going to have any hope of using these skills in a real job, you had better be comfortable with writing Python code outside of Jupyter Notebook. You would also better be aware that there's actually zero difference between writing code in a Jupyter Notebook and writing code in IPython or the console. Here's one example I like of how you might use Python in the quote-unquote real world. Let's say you write a script that emails your boss to tell him you're going to be late for work. And let's say you don't actually want to send this email manually, but you want it to get sent automatically every Friday morning so that your boss doesn't yell at you for coming into work late after you had partied too hard Thursday night. Well, that's very simple. All I have to do is, on my server, create what's called a cron tab. In it, I just enter the code for when I want this command to run, and then to the right of that, I specify the command that I want to run. That's just Python space and then the script name. As you can see, it's simply how you would run this Python script from the command line. And now, every Friday at 9:45 a.m., this script is going to send the same email to your boss to tell him you'll be late. Well, let's not get off track here. The point of this is, you really don't want to be using Jupyter Notebook for something like this. I think one perceived advantage of Jupyter Notebook is that you can see the results of intermediate calculations. However, this is merely a perceived advantage and not a real advantage, because you can do the exact same thing even when you're not inside Notebook. Firstly, as I'm sure you've seen by now, IPython also prints out the results after you enter a command. IPython is called a REPL, which stands for Read Eval Print Loop, and that's generally what they all do, no matter what language you're in. So whether that's Python, Ruby, PHP, or any other language. The keyword here is print. Why is that? Well, one of my golden rules for writing and debugging code is when in doubt, print it out. I can't tell you how many times I've gotten a question on the Q&A when it could have been easily answered by inserting a print statement into the existing code. Anyway, what's the point of this long discussion about printing things out? Well, it's that if you think Jupyter Notebook is the only program that helps you do this, you need to expand your horizons a little bit. You should, in fact, always be doing this. If you're not using an abundant amount of print statements while coding, you are not doing it right. Remember, programming is not philosophy. You're not supposed to be running a program in your head. That's like trying to do long division in your head when you have a calculator in your hand. So just by printing things out, you can be more efficient. Stop trying to guess what a program will do, and just let the program itself tell you what it's doing. The key takeaway here is, you should always be printing things out. The fact that Jupyter Notebook shows you the result of each block of code is not simply a happy surprise. But another important lesson here is that if you want to use Jupyter Notebook, there's absolutely nothing stopping you from doing so. In other words, using Jupyter Notebook is 100% compatible with everything we are already doing. In fact, if you recall, your goal in these courses is not to run my code, but to write your own code. And of course, since it's your code, you can write it however you want, including Jupyter Notebook. In the rest of this lecture, I'm going to prove to you that you can take any script from our course repository, which we know runs in the console, because that's how I always demonstrate it, and show you that this exact same code runs in Jupyter Notebook. Let's begin. Okay, so let's say I'm in the folder NumPy class, and I'm interested in the code inside classification example.py. As you can see, what I have right now is this code inside a text editor. Now, if you're not aware of what a text editor is, it's just a program that shows you the contents of a text file and lets you edit those contents. It's the ideal program for writing code. Now, occasionally, if you're writing in a language like Java or Swift, you might want to use an IDE, but even then, it's totally optional. These days, I prefer to write Java in a plain text editor like Sublime Text as well. In any case, normally, one does not need to use an IDE for writing Python code. Now, about Jupyter Notebook. Well, let's start up a Jupyter Notebook. So I'm going to go Jupyter Notebook. All right, so now I've got Jupyter Notebook running, so I'm going to start a new notebook. Also, notice that we started the notebook in the same directory as the relevant Python file. So that's something you want to keep in mind for the future. Now, at this point, what I'm going to do is I'm going to prove that everything in this Python file works exactly the same in the notebook as it does in the console. So let's start with the imports. Actually, let's grab this one too. All right, paste that in, run it. So everything's fine so far. Now let's load in the data. Okay, we've loaded in the data. Now I'm not sure what its type is, so I can check it by using the type function. So let me try that. Cool, so I get sklearn.utils.bunch, so that's the type of the variable data. Now previously, you recall that we did this example in IPython, but as you can see, the result is the same in Jupyter Notebook. Alternatively, if you wanted to run this Python file in the console, so you wanted to type, let's say, you wanted to type in Python classification example.py, then you could just add some print statements if you wanted to show those same lines while this file was running. Now, I'm not going to go through such elaborate detail for the rest of this example since you've already seen it, so let's just get through the rest line by line. Let's say I want to check out the keys in the data variable. Okay, looks good so far. Let's check the shape of the data attribute. Okay, looks good so far. Let's check the targets. Okay, still what we expect. The target names. Looks good. Target shape. It should be 569, yep. And let's check out the feature names. Okay, that's the same as well. Now let's do our train test split. Okay. Now let's instantiate and fit our model. All right. Now let's check the train score and the test score. All right. Now let's see how we can make new predictions. So you see how if you assign to a variable, it doesn't print the result. But if you have an expression, then it does print the result. So those are some predictions, and this was an alternative way to calculate the accuracy of the predictions. So we get the same answer as before. And we also have this other example where we can use a neural network to do the same thing. So let's build the model, train it, and print the train score. And let's print the test score as well. All right, so everything works the exact same way as it does without using Notebook. Now, another thing I could have done was I could have just taken this whole thing and copied it and pasted it in and run it. So that's another possible thing you can do. But the downside of that is you don't get to see the intermediate outputs. But again, that's what print statements are for. All right, so what can we conclude from this exercise? Well, we can see that this code runs exactly the same inside Jupyter Notebook as it does everywhere else. That's why I always say Python code is Python code no matter where it is. If you want to use Jupyter Notebook to run the course code, there's absolutely nothing stopping you from doing so. Hey everyone, and welcome back to this class. This is a short lecture to explain that you are free to use whichever version of Python you want in this course. Just one side note before we begin. While I've updated all the code in the repository to work with Python 3, you still need to git pull to ensure that you have the latest version. I know that some people fork the repo on GitHub, but I strongly recommend not doing this as you won't get the latest updates as easily. If you do have a fork, consider just getting rid of it, or at least make sure you pull the latest changes often. A lot of people consider Python 3 to be the new version of Python, and therefore it's the one everyone should use, but that is a very limited perspective. First, Python 3 is actually not that new. In fact, at the time this lecture was made, 2018, Python 3 is almost 10 years old. In fact, Python 2.6 was released at the same time as Python 3. So Python 2.6 and Python 3.0 are actually the same age. Some people think that because 3 is a bigger number than 2, that means we should use 3. Of course, you can see why this is a somewhat superficial way of reasoning. The bigger issue is this. If you join a large company using Python today, and they built their technology stack many years ago, they are probably using Python 2. And if you're in a large company, it's not easy to just recreate your entire codebase. That might take months or years of effort. No reasonable company that makes millions of dollars per day is going to halt their operations just so they can switch Python versions. Consider your choices if you are a manager or a business owner. You have a list of things to get done. Your clients want these things done, and they're going to pay you lots of money to get them done. So if you have a choice between your engineers working on something that will make money versus working on something where you not only get paid no money, but that actually costs you money because you have to pay the engineers to do the work, which are you going to choose? Most people I know would choose the option to continue making money. And so for better or worse, a lot of folks are still using Python 2. That means if you join such a company, you'll be forced to learn Python 2 syntax. There will simply be no way around you having to learn Python 2. At the same time, the differences between Python 2 and Python 3 are usually trivial. For example, instead of print with a space after it, print works like a function, so it has to have parentheses. Another example is that we use range instead of xrange, which both return generators rather than lists. In Python 2, range returns a list, which can be inefficient, so we try not to use that when we're using Python 2. In Python 2, division using a slash can do different things depending on what its arguments are. So for example, if both the numerator and denominator are integers, then the result will be an integer. But if at least one argument is a float, then the result will be a float. This is the same way division works in C-style languages, so it's pretty typical behavior. In Python 3, a slash always does float division, so even if your numerator and denominator are both integers, the result will be a float. If you want to do integer division, you have to use a double slash. Other examples are given on this page on my website, lazyprogrammer.me/python 2 to 3 tips. Of course, aside from these things, there are a lot more less frequent discrepancies you may come across. So if you come across something that doesn't work, you're encouraged to use the Q&A since that is the best place for you to get help. However, you most likely won't need help since the changes are trivial 99% of the time. So there's no need to give up if you see that the code you're working with is for Python 2 and not Python 3. Most likely, just a few lines need to be changed as per the error messages you get, and you'll be up and running in no time.